Hello, everyone. In this video, we will discuss derivatives of vector-valued functions. Derivatives of vector-valued functions. Suppose R is a vector-valued function defined with differentiable component functions f, g, and h. Please refer to the following 3D space. Consider the space curve of a vector-valued function, where the arrowheads point to the direction of increasing parameter. Let P be a point where the parameter is t, while Q be a point where the parameter is t plus delta t. The position vectors of these points are r of t and r of t plus delta t, respectively. As delta t approaches 0, which means t plus delta t approaches t, r of t plus delta t approaches r of t, while the difference vector approaches a vector that touches the curve at only point P. The vector that touches the curve at that one point is called r' of t, and it is the derivative of r with respect to t. The derivative of r with respect to t is defined by the limit of the quotient of the difference vector and the change in parameter that caused the difference vector, as the change in parameter approaches 0, for all parameter t where the limit exists. Even though this illustration is for delta t greater than 0, the concepts are also valid for delta t less than 0, which means r of t plus delta t would be coming from the other side of r of t. Nevertheless, the direction at which r' of t points remains the same. From our previous discussion, the limit of a vector-valued function is computed from the limit of each component function. Hence, the derivative of a vector-valued function can also be written as the derivative of each component function. Geometric properties of the derivative. Consider a point on the curve where the value of the parameter is t0, and r of t0 is the position vector of the point. r' of t0 is the tangent vector to the curve defined by the vector-valued function r where t equals t0. In the figure, the vector r' of t0 is tangent to the curve at point P where t is equal to t0, and it points to the direction of increasing parameter. Meanwhile, r tangent of t is the tangent line to the curve defined by the vector-valued function r where t equals t0. In the figure, the line r tangent is tangent to the curve at point P where t is equal to t0. The equation of tangent line is given by the following vector equation. The first term is the position vector of the point where the line is required to pass through, while the vector in the second term is the direction vector of the line. Note that the discussion on the previous page is a generalization of the discussion here, which is focused on tangent vector and tangent line at a particular value of the parameter. T is the unit tangent vector which points to the direction of increasing parameter, just like r' of t. In the figure, the unit tangent vector points to the same direction as r' of t, the direction of increasing parameter. However, its magnitude is equal to 1. It is computed as the tangent vector, or the derivative of the vector-valued function, divided by its norm. Consider a vector-valued function that has a constant norm for all values of the parameter. This means that the space curve lies entirely on the surface of a sphere, which is a surface that consists of all points that have equal distances from the center. Please refer to the following 3D space. Consider a space curve that lies on the surface of a sphere. Differentiate both sides of the equation. Apply the product rule on the left side, and use the constant rule on the right side. The result is that the dot product of the vector-valued function and its derivative is equal to 0. This means that the vector-valued function and its derivative are orthogonal for all values of the parameter. Going back to the figure. For any point on the curve, the length of the position vector is the same as the radius of the sphere. Because the length of the position vector is constant, we can conclude that for any point on the curve, the position vector and its derivative are orthogonal. Example 1. Find the tangent vector, the tangent line, and the unit tangent vector of the following vector-valued function where t equals pi over 3. Solution. First, let us find the derivative of the vector-valued function. Apply the product rule as well as differentiation rules for algebraic and transcendental functions. Then substitute t equals pi over 3 to get the tangent vector at the given value of the parameter. Therefore, this is the tangent vector to the curve where t equals pi over 3. Next, find the equation of the tangent line. Substitute the required expressions, the vector-valued function and the derivative at t equals pi over 3. Evaluate the values of the trigonometric factors. And combine the expressions for I, j, and k. Therefore, this is the vector equation of the tangent line to the curve where t equals pi over 3. Finally, compute the unit tangent vector where t equals pi over 3. The tangent vector for t equals pi over 3 has already been found earlier. Meanwhile, this is the formula for the norm of a vector. Thus, this is the unit tangent vector to the curve where t equals pi over 3. Its magnitude is equal to 1, and it points to the same direction as the tangent vector, which is the direction of increasing parameter. Please refer to the following 3D space. This is the graph of the parametric curve defined by the given vector-valued function. It is called an Archimedes spiral. This point is where the value of the parameter t is equal to pi over 3. This is the position vector of the point. This is the tangent vector to the point, while this is the tangent line to the same point. The unit tangent vector is the unit vector that points to the same direction as the tangent vector, and they both point to the direction of increasing parameter. Example 2. Show that for a spherical spiral given by the following vector-valued function, the vector-valued function and its derivative are orthogonal. Solution. Differentiate the vector-valued function. Apply the product rule for products and the chain rule for composite functions. And use trigonometric function rules. Then find the remaining derivatives using an inverse trigonometric function rule. And simplify. Afterwards, take the dot product of the two vector-valued functions. Multiply the factors on each term. Notice that we can combine these two expressions by factoring and cancel out these two expressions. Use a Pythagorean identity. Which leads to the cancellation of the two remaining expressions. Hence, the dot product of the vector-valued function and its derivative is equal to 0, which means they are orthogonal. Please refer to the following 3D space. The graph of a spherical spiral is located on the surface of a sphere, which means the norm of the position vector of any point on the curve will be a constant equal to the radius of the sphere. Thus, it follows that for any point on the curve, the position vector and its derivative are orthogonal. Example 3. Prove that the derivative of a cross product is given by the cross product rule. Solution. First, substitute the vector form of the cross product of two vectors. Then take the derivative of each term with respect to t by applying the product rule. The result can be grouped into two vectors, one vector where the component functions of vector u are differentiated, and the other vector where the component functions of vector v are differentiated. The two vectors follow the vector form of cross product. The first vector is the cross product of the derivative of vector u and vector v, while the second vector is the cross product of vector u and the derivative of vector v. Thus, the derivative of the cross product of two vectors is given by the following formula. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.